Good morning, everyone, and thank you for joining us for our What's New in PFC 9 webinar. My name is David Dugagne. I'm with ITASCA Minneapolis. I'm responsible for technical marketing. And today's presenter is Matthew Purvance. Dr. Purvance is a software engineer with a background in mathematics, mechanics, and geophysics, specializing in algorithmic development and implementation. He has participated in the design of ITASCA software for more than 16 years. Before we get started, if you have any questions, there is a Q&A icon at the top of the Teams meeting screen. So if you click that, you'll be able to type in your questions, and we will respond to them as best we can after the presentation. So, Matt, if you'd like to proceed.
Sure. Thanks, Dave. I appreciate it. Hi, everybody. I'm Matt Purvance. As Dave mentioned, I've been with ITASCA for a while now, and I started working with the development of PFC 5 and have continued with PFC throughout the years, and also been associated with many of the other products that we offer. But today I want to discuss the new features in PFC 9. So there's my email address. It'll be available at the end of the presentation as well. I'm pretty much the main PFC developer and support provider. So if you have questions, please contact me either through this email or the PFC technical support email, which I'll show at the end of the presentation. Okay, so getting started. The new features in PFC 9. I'm going to touch on what I think are the most important features as a developer for the majority of users. That's definitely not everyone, but I see through the support what people tend to be doing. So first, I'll touch on the user interface update, which is substantial in PFC 9 relative to PFC 7. And just to be clear, we skipped version 8 in the sense of we went directly from 7 to 9. Due to one of our other products having a version number of 8. So this is the next version after PFC 7. Then I will discuss the Python update that's in PFC 9, speed improvements, which I'll discuss why they're ongoing, the Subspring network contact model, which is specifically talking about bonded block modeling with rigid blocks. There may not be a lot of you using rigid blocks for bonded block modeling, but I think it's quite useful and exciting to model solid rock, and structural elements, modifications to structural elements. So starting with the user interface update, and I will actually show the user interface to discuss some of these things. So the first thing that I want to discuss is the reorganization, which includes a tabbed commands area, a workspace, which can be split, and it includes now the control panel as part of the workspace area, and what we call the object tree. So I will open up PFC version 9 here with a project opened. So you can see that this has a lot of similarities to PFC 7. It's not just a color change, though. We've changed the design of the user interface quite a bit, and we think it's substantially better and helps with ease of use. But definitely, if you have feedback, please, again, contact me with your feedback for things you like or dislike. So, as I mentioned, there's a workspace area. So this whole area that has data file, a plot, and what we call the control panel or control sets is the workspace. This is the commands area at the bottom, and on the left, the object tree area. So one change that you'll notice right away is we have these 3 buttons in the lower left-hand corner, which allow you to dismiss, for instance, the commands area or hide it, the workspace area or the objects area, if you don't want to utilize any of these spaces when you're doing simulations or modeling. The tabbed commands area allows you to, so unlike PFC 7 where we had tabs, and you could put a bunch of different things in the tabs next to each other. This commands area has tabs which are restricted to only belong in this area. and they can be split. So for instance, with this little arrows here, you can split the Python, the IPython console, to one side and have the regular ITASCA PFC console on the other side so that you could visualize them both at the same time. This can be really useful depending on the types of simulation that you're doing. The workspace area. So the workspace area, again, before was constituted by a number of tabs. You could have an arbitrary number of tabs open. We've changed this, and in addition, I should say that you could float tabs. You could have tabs floating. We do not allow for floating anymore due to some issues, performance issues, which we were having in the user interface. And instead, what we allow is splitting of these panes. So for instance, we have one pane open, which is showing a data file. We can use this splitting tool to create new panes that can then, with this context tense selector, be populated with plots or with data files. And there's not a limit in the amount of splitting that somebody can perform, right, in this area. So you can set the user interface up with data files and plots in PFC9 in a way that's conducive for your working strategy, right? I've seen many people utilize different layouts, and this gives you a lot of flexibility in the layout. Along with that, this console, or the control panel area on the right, that gives you controls, and this has been reorganized. So for instance, this plot has focus, you can see the blue color, and the controls are associated with this plot over here. And we've separated those into sets. So there is a set for plot attributes, for view shift, and for fish global variables, which is different as well. And additionally, a set for our help, encode help. So that is a quick overview of how the areas have changed. And as I didn't really discuss the object tree, I'll discuss that in detail now. So the object tree on the left-hand side, that's much different from PFC7. Whereas before we had 3 boxes, which allowed you to control data files, plots, and save files, and results files. Now we have a tree, which allows for, we think, more efficient navigation with right-click capabilities, drag and drop capabilities. There's help integration into this tree and model information. We think that this is quite new and useful for many of our users. So looking over at this object tree area, I will say that I would suggest, you can see this little help button for contextual help at the top of the tree. If you press this button, which I already had, a description of the tree, of the objects panel, the objects tree, is brought up into the help. I would suggest reading this when you start using PFC9 because it has a lot of very useful information about how this has changed. First, I'll start with the project branch on the tree. So as in PFC7, where we had access to our data files, projects, or plots, and save files and results files, these are now presented in a tree format. And really, to figure out what you could do with any of these items in the tree, I strongly suggest start playing with your right mouse click on elements in the tree, because it will give you all of the information about what's available in the tree, right? What you can do, what operations you can do on an item in this entry or this level of the tree. So, for instance, in the data files, you can create a new data file, open a data file, add one to the project, and all of these are hooked up to help. So for instance, we could be on the project pane and either push F1 or go to the help, and there's a description of the project branch for you to read. And I would suggest reading these again so you could understand in more detail what each could do. As I mentioned, though, there's double-click capabilities. So double clicking, the behavior of an element is in bold, so open in workspace. So if I double click on, well, step 2 contact, the pane that has focus over here, that will be opened in that pane. So if I gave focus to fragments and I double clicked on tests, test is open there. More importantly, and I think more intuitively, we've added drag and drop capabilities over to the projects, not just the projects area, but this whole tree, which I'll discuss what that means in the model state information in a moment. So it becomes much easier. So I'm going to close some of these panes, and it becomes much easier to lay a project out in a way that you might find useful. For instance, I could create a new data file by dragging it over here, and I'll just call it new. So that just created a new data file. I could then split this data file because I also want to see step 1 by dragging it close to the boundary. And that allows me to reorganize the user interface just by drag and drop operations. And I could also do the same thing by dragging a plot over here to move a plot into the user interface. So we think that this drag and drop capability is pretty intuitive, pretty easy to use, and pretty useful. With save states, it doesn't make a lot of sense to drag them into the user interface, into this area. So you can see that dragging is disabled, but you can drag that into the commands area and onto specifically the console. And when you do this, that causes the save file to be restored. I'll mention one other really useful thing about new save files in the system. If I right click on a save file and I want to get information about the save file, that's one of the entries here. Meta information is saved. I'll close the model and programs, so I'll discuss that in a second. But meta information is saved in the header of all save files in PFC9 that allow you to relatively quickly query when it was created and information about the model, actually. So it gives you a way to catalog, to go back to your save files and not have to reload them to actually see what's in the save files. This is the projects branch, and below that is the model state branch. This is something that's completely new to PFC 9, and I should mention that if you don't like any of these, you can turn them off up here. So I could remove the project, the model, the program, or the watch branches, and if I do, for instance, the model state, it just is hidden. So if you don't like these additional features, which we're discussing in the user interface now, you can turn them off and not be bothered by them. The idea behind the model branch is it actually gives you information about the model that you have currently loaded in PFC9. So in this model, there are 8,978 contacts. It gives you information about the CMAT, about fish symbols or functions, about rigid blocks. Also some meta information. These are organized similar to commands. So for instance, under the R block, there's an R block attribute command, and it gives you a textual description of all of the things that you can set or get using the R block attribute command, right? And not only can you do that, what is interesting is that, say, for instance, you want to visualize the velocity of the rigid blocks in this case. You could take this and drag it over to a pane. And in this case, this was a data file. So it's going to ask to create a new plot, and I'll call it velocity. And it plots the rigid block velocity. I'll close the others, right? You can also get help about the commands associated with this. So for instance, the R block attribute command, if I right click or if I push F1, here's help information about the R block attributes. We believe that this combination of visualization and help and explorability, you can explore this information about what's in your model at any time from this model information over here. I think that really helps people to see what's in their model and to identify places where their models could be improved or missing. The programs branch, very similar thing, except these are program related commands. And then finally, the watch branch, I'll just mention briefly, allows you, I'm only interested, for instance, in seeing what the convergence is for all the rigid blocks in the model. You can right click and add this to the watch list. So instead of having to drill through That, or for instance, I'm only interested in looking at the value of the broken fish symbol. These, instead of having to drill through those lists, these are up front in a watch list, right? So yeah, there's a lot over here. Histories are really cool, I will say, because you can plot a history the same way. You can do, there are many operations such as this. So I know I've discussed this for a while. I'll remove the histories. I'll move on to the next item. Please explore this and ask questions if you have questions. So that's the object tree. Quickly, I'll mention the example dialog improvements. So in the code, through help examples, we've greatly expanded your capability to search through our examples and find information about the examples. So you can search, all of the codes are included together in the distribution. So you can search for help in any of the codes. In this case, just PFC 3D is selected. You can search for text in those examples. You can also filter the examples out, the names of the examples here. You can open them with a code and it will copy them to a new location and open a new instance of PFC. So this also helps people to get into the code, we believe, much, much faster. And going back, inline help has been greatly overhauled and it has a new filter and search capability. So whether or not you're aware, if I have a data file open and I'm looking for information about the model domain command, I could either press this button on the right-hand side, or I could do Control Space. And if I do this, this opens the inline help utility. Please push this help button and it will give you a reference about how it works. If you're not familiar with this, it's super useful for creating data files and understanding examples. But we also allow you to search for examples that have these commands in them and to filter the inline help itself. So we find that's very useful, especially for people coming into the code that haven't used it much before. And finally, plot information using Q. One of the things that kind of always bothered me in PFC is that when you want to get some information, you can see this information area on the lower right is away from where the plot is and from where the cursor is. Instead now, if I'm on the user interface and I push Q, that information is displayed close to the cursor. I can also press C to pause it, so this information stays there and you can copy from here. You can dismiss it with either pushing escape or the X button, and you can push Q again. So find this capability very easy to use and again, quite useful. Moving back to the presentation, I know I spent a fair amount of time talking about the user interface improvements, but it is pretty substantial. We do believe it is very useful for especially new users and for existing users. I am biased. I was one of the developers of the user interface upgrade. But if you have questions or comments, please contact us. We would love to hear from you. So the Python update, quickly, I'll just mention, we've moved from Python 3.6.1 in version 7 to 3.10.5 in version 9, which is still behind 3.13, which is the most current, but it's a pretty big upgrade. The next major release, which will be PFC 10, will update to the most recent Python. When that is going to happen is yet to be determined. So if you're not aware, the Python package that we include is a curated Python environment that includes things that we think are really useful, like matplotlib, libraries like matplotlib, NumPy, for data analysis. And it includes custom bindings to PFC elements. So you can get balls in Python. You can operate on balls. You can operate on contacts or walls, for instance. In addition to that, we have libraries which do other things, and new libraries that have been included, which I wanted to mention, are Bodo 3, which allows you access to AWS, DebugPy, which is for debugging Python. We didn't have that in version 7. EasyDXF, which is a DXF utility. Futures, which we did not include in version 7, I don't believe, which allows you to adopt new syntax, and Pandas, which is not a very big library, but can be really helpful for data processing. So that's all I will say about the Python update. moving on to speed improvements, the main feature besides the user interface is a rewrite of many of the engine components in PFC 9 from PFC 7. And to give everybody a boost, hopefully, in the performance as they're running models. So what have we done? We've actually taken a very different design approach to the underlying data structures. So this is transparent to you as the user, but I do want to touch on it because it is important. We've gone from an object-oriented approach where you have a ball and a ball holds, for instance, its position, velocity, volume, radius, holds all of this information in a data structure under a ball, the same with a contact. We've changed that to adopt a structure of array data storage model. So basically, instead of having an object, which is a ball, which holds all of its data, now we have an array of all ball radii, an array of all ball positions, right? And so it's a very different access pattern, and data access pattern, and it required a complete rewrite of the computational parts of the engines. Again, this is transparent to you as the user, but hopefully you'll see the benefits of this. And I'll show you some speed performance numbers in just a minute, some speed up performance. This has been applied to balls, clumps and pebbles, and rigid blocks, and also to ball, pebble, and R-block contacts. It has not been applied to everything, but in general, from what I've seen, people are running models that are all balls, all clumps, or all rigid blocks. And really, contacts with walls are unimportant because they are usually just on the boundaries and they tend to be few, right? There is a change to the contact model interface because we are not just storing the pieces, the balls and the clumps and the contacts differently, we're actually storing the contact models differently as well. So if you have a user-defined contact model that you're compiling, there is a new method that needs to be overwritten. And you can see it in our examples, but it's important to note. So this new storage strategy, what it ends up doing is it allows you to sort the data, sort model data, so that, for instance, balls that are close to each other in space, you can sort them so they're close to each other in memory space as well, in a much more streamlined fashion than you can with an object-oriented approach. You could do that in that approach as well. It's not only the sorting, it allows you to only access the data which is necessary for the computation that you're doing. So when you're doing equations of motion, you don't care necessarily about the ball groups, for instance. So in this way, it allows you to only access the information which is going to be used for the balls when you're using it. But it also allows for this sorting mechanism. This is done automatically. The sorting is done automatically. And you'll say, well, why do I care how the data is stored in memory and if it's sorted? You care because for balls and clumps especially, the computations are bounded by memory bandwidth. So if you can keep the memory closer to each other in memory space that you're wanting to access. So for instance, if you have two balls that are in contact with each other, one ball started in the lower left-hand corner of your model, one in the upper right-hand corner, they weren't created in the same memory space potentially. And as you create a contact that's in a different memory space and a contact model in yet a different memory space, if you could move those in memory space that are now close to each other so that in memory space they're close to each other, then when you're processing the force displacement law, it'll be faster. And this is this ends up providing a pretty big performance boost in many cases, not in all. As I mentioned, this is transparent to users. There is about a 15 to 20% increase in memory, which is a downside. You can't switch back to the old way, so you're going to have to live with it, but I think you'll be happy with the performance increase. And also show some speed up results on Windows on not a particularly fast machine, but a 10-core 20-thread machine, an i9-9820X, a little bit older CPU. And these results are very similar on Linux as they are to on Windows. So I'll start with just a very simple example, balls in a box. So just generating distributing balls. I shouldn't say generating, because we're using the ball distribute command to create overlapping balls in a box with has a wall boundary on it. So there's about 165,000 of them. And I'm going to use the linear contact model and a wall boundary. I will cycle, so it's using all the threads. I will cycle 100, cycle 1000, calm 100. So this means that every 100 cycles, I'm removing all of the velocity and spin, if there was any. So rotational, translational velocity, if there was any rotational velocity, because the balls are arbitrarily overlapping to start with. This might be the first step in a material genesis process to create a specimen of balls if you're doing bonded particle modeling, or this might be you filling a container up and allowing the particles to equilibrate for a shear box test or something like this, a granular flow test. This is almost always how we start with balls, right? Something along these lines. And I'll really look at the model performance during the second set of cycling down here, this cycle 3000. So this figure in the upper left is a screenshot of this Windows machine. I'm on Linux right now, so the user interface might look a little different. But this is the Windows box. And this is the CPU performance with PFC 7 cycling. And this is at 1,000, after about 1,000 cycles, and this is after about 3,000 cycles. So you can see as the particles are moving, this is a very dynamic model, the thread performance is diminishing. And this is largely due to these L3 cache misses, because as the balls are moving around, you're creating new contacts. Balls are moving relative to each other. They're moving around. They're in this kind of memory space for which they were created, but they're sort of decohering. The memory is decohering as you're creating more and more contacts. This is in PFC version 7. And towards the end of about 3,000 cycles, you can see that the total thread utilization is at about 60% PFC 7. This was the same in PFC 6 and PFC 5. Up the upper left now, I'm showing that same figure for PFC 7 after about 1,000 cycles, and this is now PFC 9. You can see that there's a large drop here in thread utilization. It went to a single threaded operation. This is actually the sorting that's happening. So this sorting is happening on a single thread because it's moving things around in memory. It's being triggered by the number of contacts that are being created and destroyed, or by the number of pieces. In this case, if we were to create or destroy a bunch of balls, it might trigger a remap. So it's not happening all the time, and it's not happening if you had a static assembly where you're not adding or removing things from the model, right? So there's no additional overhead. It's being triggered, and we've played around with this a lot in terms of performance. It's being triggered when things are dynamically happening. And you can see very clearly that the thread utilization is quite high. And in fact, if you go to 3,000 cycles, the thread on PFC 9, which is what this is showing, the screenshot is showing, the thread utilization is near 100% because of this sorting. So I also output the number of balls, contacts, and so these are active contacts and inactive contacts. So you can see that they're not identical with each other. Of course, they might not be, because when you switch compilers, which this is using a different compiler, you don't get the same answer. But the answers are deterministic for both PFC 7 and PFC 9, meaning that when you run it twice in PFC 9, or you'll get the same answer each time. There's also different data structure, so this can sometimes cause differences in the answer, quote unquote. But they're all equally admissible. They're all equally viable solutions. What's most important, though, is the speed up. So in this case, almost a factor of 4 speed increase. That's a lot, right? I think it's a lot. Just without any user intervention. This is balls dynamically filling up a box with gravity, and it goes almost 4 times faster. And this is not uncommon. I've seen this in many ball-based models where you have balls that are either in large granular flows that are quite dynamic, or where you're filling up a box, for instance. So that's a pretty substantial speed up. If you take this same model, had 165,000 balls, and you just bond it in place and replace the linear model with the linear p-bond model. So this is sort of a proxy for a bonded particle model using balls. Not exactly a proxy because it's not very well connected at this point. This specimen isn't, but it gives you an idea because basically at the same time I'm removing all of the velocities, I'm removing gravity, I'm removing the contact forces. So this is really a quasi-static model. Nothing's really moving around. And there are bonded contacts and a bunch of inactive contacts. In this case, so the PFC 7 versus PFC 9, these are the run times here. The speed up is about a factor of 2. So what I'll say is that the speed up is dependent on the model, depending on what you're using in the model, and also whether it's really dynamic or really quasi-static. It's not the same uniform for model type, and I have seen differences for different processor types, right? And as I say here, the thread utilization did increase in PFC 7 due to less motion. Actually, the contact detection and the continued cell space remapping was causing some churn to happen in PFC 7 because the balls that had moved around, they were in different memory spaces, right? And that was sort of remediated when I went to a quasi-static model because that's just not really happening. Not much is moving around. So from what I've seen in bonded particle modeling, and the speed up also does depend on the contact model you're using. This is the linear p-bond. Soft bond has a few more parameters in it, so the speed up is a little less. With bonded particle models, I've generally seen speed ups about 1.7 to 2.5, but for granular flow simulations with balls, depending on the model geometry and the contact model being used, somewhere around 3 to even up to 5 as a speed up. So again, without any user intervention, no user tuning. That's just a change in the data structures. I'll show results for clumps as well, because the speed up is different for balls than it is for clumps, and with rigid blocks as well. They're different in all cases. So that very same model, basically, except using a 2-pebble clump. So it's just a dyad, just 2 pebbles that are rigidly glued together, and create about 165,000 of those and put them in a box with gravity. And so what you do see is that first off, from balls to clumps, there are 2 pebbles, so you should expect it's about 2 times slower, and it is. So this isn't comparing version 7 and 9. This is just comparing balls with either version, and this is a comparison with PFs, between PFC 7, but it's the same with 9. 2 pebble clumps are about a factor of 2 times slower than balls. That's kind of the way it is. But the speed up from version 7 to 9 is about a factor of 3, which is a pretty substantial speed up for this dynamic case. And again, I've seen anywhere from about a factor of 2.5 to about a factor of 5, depending on the number of pebbles in the clump, depending on the clump geometry and how dynamic it is. Speed up from version 7 for version 9 to version 7. For bonded clump assemblies, the speed up, again, same model, just as I did with balls, bonding them together and removing all the dynamic motion, about a factor of 2 times speed up. And again, it's about a factor of 2 times slower to have 2 pebble clumps than it is to have balls. And that's not comparing between versions, that's in one of the versions, so you would expect. So speed up a factor of about 2, which is still a fair speed up. So that means, it'd take about half the amount of time to do the same simulation. For rigid blocks, the story is a little bit different. And so whereas I was getting speed up, so this is, again, a very dynamic case. Rigid blocks are blocks in a box. And here they're just boxes. So they're cubicle shaped rigid blocks, and I'm just generating about 150,000 of those, 160,000 of those, same as the other models, and allowing them to fall under gravity. The contact detection and resolution for rigid blocks is much more computationally expensive than it is for balls or for clumps. And so where balls and clumps were very much data limited, or memory limited, I should say, rigid blocks, they're also somewhat memory limited, but they're computationally limited, right? It's a much more expensive computation to do the contact resolution. So the time to run this simulation was about 582 seconds. Comparison to clumps, which was about 606 seconds. So it's about the same as a 2-pebble clump using rigid blocks, so not drastically slower, at least in PFC 7. And version 9, the speed up though is in version 9 it's about 235 seconds. Where it is a little bit faster again. So the speed up ends up being somewhere around 2.4, 2.5, right? Again, not a lot. I don't think many users from what I've seen are using rigid blocks for granular flow simulations because of their overhead, and not a lot of users are doing bonded block modeling. But they're more, this is also trying to demonstrate to you that if you're wanting to use multi-pebble clumps, rigid blocks, if you can use convex polyhedra in your model, they are a viable alternative to clumps in their performance for these sorts of very dynamic granular flow simulations. For bonded block model, though, you don't develop bonded blocks quite the same way that you bond balls or clumps together to make a bonded particle model. Instead, you go through a meshing operation with rigid blocks usually to create a zero porosity packing of rigid blocks to start with, and then you bond those together and cycle them. So I took the tunnel bonded block model from the documentation set and ran it in version 7 and version 9. I was surprised by this because most of the performance comparisons I've actually been doing until I started getting ready for this presentation were comparing PFC 9 before this data structure change to after this data structures change. And I can say that there have been some changes to the way PFC 9 does some computations with rigid blocks, especially during cycling relative to version 7, which are more robust. So when comparing from version 9 before the change in the data structure to after the change in the data structure, the bonded block model runs faster by about a factor of 1.2 or 1.3. Comparing with PFC 7, though, it's actually a little bit slower. And that's why I'm going to say it's a work in progress. That I just discovered this. I think it's because of other modifications that have been changed to the rigid blocks and when they're bonded to make them more robust which are not in version 7. But the model is very close to the same speed. I have run a few other models where the speed was almost identical between version 7 and version 9 with this new data structure too. So I'm trying to give you an idea that the speed up results are a little bit, it's not necessarily guaranteed. I think for the vast majority of what you're using, what most users I see are using PFC for, there's a big speed of performance. This is still a work in progress, though. So not only do we have this sort of speed up, there's an example in the documentation which talks about granular flow simulations specifically and speed up there by changing contact detection parameters and changing time step to be fixed. And so in this case, and read this example in PFC 9 if you're doing granular flow simulations, I was actually, this example is trying to simulate the Brazil nut effect, where you have large particles become buoyant in a smaller particle bed. What's interesting about this is by user intervention, now by you tuning the code, I was able to get almost the same model response, but speed up the performance by a factor of 3 by changing these parameters. So I would strongly suggest taking a look at that new example and some of the new contact detection parameters which we've introduced that you can play with. But again, that requires user intervention. Two last final things. I'll talk about the Subspring network contact model, which is really new in PFC 9. This is for bonded block modeling, which would be something similar to what you would use 3DEC for, where you're trying to simulate, say, the response of a tunnel to excavation or a synthetic piece of rock that's being broken due to, and that's what I'm showing here, due to laboratory tests. And what's different about this model from the Spring network model, which was in version 9, is that it allows for 3 subcontacts that can fail independently of each other. So kind of in a way in 3D, similar to a flat joint contact model. And this allows for a much more realistic failure response. As with the Spring network model, you can just set the material constants if you want them to be uniform. So there's no calibration for the elastic response, the Young's modulus and Poisson's ratio. Those are just specifiable, which is very different from bonded particle modeling. And what's really excited about this model is this, what I'm showing in this plot. So this is a tetrahedral model, about 14,000 rigid blocks, I believe. I am up here in the upper right, I'm showing a direct tension test. So these pink discs and triangles are bonds that have completely broken, meaning all 3 subcontacts have broken in tension. The pink is tension, green is shear, and the red are mixed mode. Since there are 3 subcontacts, they could all break in one mode, tension or shear, or you could have a mixed mode failure. And there's a distribution of strengths in this model. On the right, I'm showing a stereo net of the orientations of these breakages. And in this case, meaning if the points are plotted in the center of the model, it means that the breaks are horizontal, right? Subhorizontal. And if they're on the exterior, it means the breaks are vertically oriented, right? So you can see that there's a nice through-going crack that forms actually in the direct tension test, and almost all the breakages are subhorizontal. That's what this stereo net plot means. Down here, I'm showing a UCS test, so unconfined compression test, where platens are squeezing from top and bottom. Here, there are very few breakages that are subhorizontal, but most of the breakages are nearly vertical. So this is consistent with tensile, vertically aligned tensile cracks. And what's really cool about this is this plot down here. So this is a fragment plot. So that means, for instance, all rigid blocks that are colored in orange are still bonded to each other through at least one contact being bonded, right? So you can actually see the development of what look like sort of shear planes in this 3D model. To my understanding and to my knowledge, there are really no models that can produce this sort of behavior in 3D. In 2D, yes, but not in 3D. So I know a lot of people aren't doing bonded block modeling that might be listening, but this is, I think, a pretty decent advance in bonded block modeling technology. And I would, we also have a paper that we're hopefully submitting on this using Voronoi tessellation instead of a tetrahedral tessellation, but very interesting, I think. And finally, structural elements. I think most users out there aren't even aware that they could use structural elements with PFC or even understand what structural elements are. And for granular flows, it may not be interesting. But there are some new features here, which I'll describe, which could be useful, especially for bonded particle or bonded box simulations. They could also be useful in granular flow simulations. So the structural elements, these are basically finite elements. And there are sort of 1D elements like beams or cables. And there are in 3D, there are 2D elements, which are shells, finite element shells. They can be used with balls, clumps, and rigid blocks. They really can be. They could have been used since PFC 7. In PFC 9, they can be used with your PFC key. You don't need a special option or anything like that. They can be used. What's new in PFC 9 is that there are now nonlinear models that have been implemented into the structural elements themselves, so they can fail and have a plasticity response. This was not available before. And we, saying ongoing, there's some ongoing work with 2D structural elements as well. So the next release, not the current one that you can get from the website, but the next one will have 2D structural element links for balls, pebbles, and rigid blocks. So that means you could have a piece of rebar, for instance, embedded in a soil. And how that actually works is there's a rigid connection between, for instance, if it was a ball, the soil was being modeled as a ball, between nodes of the structural element and a ball, and that acts as kind of a surface, and motion and forces are given between the balls and the structural elements. So it's acting as another strength element inside the model that itself can fail, especially with the new nonlinear models that have been implemented. At the moment, we don't have liners in 2D. So in 3D, we have the ability to use a shell. And there's an example in the documentation which uses a structural shell as a triaxial confinement sleeve for a triaxial test in 3D. That capability is not there in 2D yet, but it's planned for hopefully not the too distant future. So I think I've gone my 45 minutes. Again, please contact me. I'm Matt Purvance. You can either get me through my personal email or the PFC technical support email. I am responsible for both right now. The user interface has changed a lot, and we think it's it greatly improves user experience, but we'd very much like to hear from you if you have any feedback about it, whether you like it or don't like it, or ideas for what could be changed or different. And we do think the speed improvements are pretty substantial, so for the vast majority of models, but that work, as I said, is ongoing. Yeah, so that's, I think, everything that I have to say. And if there are any questions, as Dave mentioned, I believe that you can type them in and he'll read them to me and I can answer them. Otherwise, please you can contact me directly if you have questions through email as well. So thank you for your attention. I really appreciate it.
Thank you, Matt. It's awesome to see all the new developments and features in PFC 9. Before we go to questions and answers, if you have any interest in learning more about PFC 9 or purchasing it, you can go to our website at itascasoftware.com. If you're interested in a free 2-week trial, contact us at sales@itascasoftware.com, and there's a QR code there. So I'll just leave that up on the screen and we'll go to Q&A. So we do have a few questions. First question is, what about PFC CFD coupling?
So the PFC CFD coupling is the same as it was in version 7. So in 3D, there still is a CFD module which allows you to have a mesh and set porosity on the mesh and velocity of a fluid. But there are no new additional developments than what you could do in PFC 7 and PFC 9 currently. And we don't have any additional developments planned, to be honest, at this point. Through the interface, though, we do have an example in the documentation that allows you to use Python to do coupling yourself. And I will say, since we have a Linux version, we had it in version 7, but with the Linux version in 9 as well, that coupling with OpenFOAM would be substantially easier than it was when previously you had to use OpenFOAM in Windows through Wine or something like this. So yeah, so no, there's been no real change to what is there from version 7.
Okay, thank you. Can PFC 9 now model a chain or cable attached to a structural element, bonded rigid blocks, that goes through the soil? This is for an offshore foundations project.
Right, so in PFC, you can use the existing structural elements that we have. So we have a cable element. We also have elements that are similar to rock bolts. that have been effectively used in a number of products, or sorry, a number of projects, using rigid blocks for the material, right, for the bulk material, and then having, for instance, bolts, rock bolts going through them to try to change the spalling response of the material as you're doing a tunnel excavation. So I'll say that yes, you can, with the existing structural elements that we have, those can be modeled with rigid blocks to do things like under water pile installation, or granular installations with structural elements as well, right? To model specifically a chain, I believe the cable element is the closest element that we have to modeling what you might say as a chain, if I understand what you mean as like a chain link or something like this. I may be misunderstanding the question, but yes, I believe that you can use what's there now to do the types of simulations that you want to do with PFC.
Great. Next question. If I use the SNEV model in PFC pre-release version, is that fine? Will it influence the computed results to some extent compared to the most updated version of PFC 9?
So what's being asked there is the Subspring network Voronoi breakable model, which is what we are currently, that we've published through mostly work with Dave Potiondi, published some works on this as a modeling methodology using Voronoi blocks instead of tetrahedra, and cutting those Voronoi blocks based on stress accumulation if you're doing something like a triaxial or a UCS test. No, so the question is have there been large changes, I believe, to the Subspring network model from a pre-release version to the final release version? No, the Subspring network model is very similar. It's effectively the same. Is there a big difference in model response with rigid blocks from pre-release to after the change in data structures? No, we've done a lot of testing to try to ensure that even though we've rewritten the computational engine for balls, for clumps, and for rigid blocks, that they're producing effectively the same response from before the data structure change to after the data structure change. So I would strongly suggest moving to the released version, not the pre-release version, and because that's the version we're supporting, that's the version that we are continuing work on. So the model response should be effectively the same.
Great. Have there been changes in water modeling?
At the moment, no. There really have not been changes in water modeling. We had planned, and we are working on a development to allow for fluids in solid materials. So allowing for pore pressures to build up and change in bonded block or bonded particle models. That is not currently included in PFC 9, and it's not planned exactly how that rollout will happen at this point. It's not been determined. So at the moment, what's available right now, no, there's not a difference. In the future, we hope we will have a pipe network pore pressure model, basically, that allows for some fluid coupling in solid materials. That won't be applicable to granular flows, though.
Okay, the last question actually has a bunch of sub-questions. So let's see how far we can get through this. In PFC 7, we can run 3 simulations at the same time. How many simulations are possible in version 9?
Actually, you should have only been able to run 2 in version 7. If you could run 3, I'd be curious to know how. With 1 license. It's the same in version 9. You can run 2 simultaneously on a machine. And that is independent of whether you're using a web license or a USB dongle.
And then a follow-up on that is, if I can speed up my simulations by 50%, but I cannot run 3 simulations, but just 2, is it really faster? So I guess I'll just comment on that in the sense of a license with a single seat should entitle you to run 2 models of PFC, FLAC3D, whatever, at the same time. There's always a compromise there. You know, as the models get larger, can you actually run 2 models at the same time? But anyhow, it's the same in 9 as in 3. So if you get a 50% speed up in version 9, you should be better off.
Yeah, and I will say too that through there's command, program threads command, which can allow you to set the number of threads. So if you still want to operate that way, I wouldn't suggest it, because in my experience, running multiple models on a machine is always slower than running 1 model that's running it using all the CPU, because you have more cache contention and memory is not as optimized. That's my experience. If you want to run that way, you can actually have 2 instances of PFC open and set the number of threads, use half the number of threads, and it will use half the computational resource on the machine. That's your choice, but you can play with it and decide how you might want to operate the code.
Well, also, Matt, PFC 9 allows you to run PFC in the cloud, correct?
PFC in the cloud. Well, I mean, so there is not an MPI version of PFC. Can you run PFC on AWS instances? Yes, you can. You have to fire up the AWS instances and install PFC. Since there is a Linux version, it's much cheaper to run on AWS instances. Yeah, so I mean, that's what I would say about running PFC in the cloud. I guess through Rescale, I think you can run PFC instances, but they do not run in MPI currently.
Right. So you can, we have a partnership with a company called Rescale, and essentially what it allows you to do is you can do it yourself, but it's quite a bit of work to set up a cloud instance on AWS. But through Rescale, they really simplify the process, and then essentially you're just uploading your data files. And as Matt said, it's not a cluster version, so we're not running 1 large model across many machines, but you're able to run many models across many machines. So if you find, rather than having to buy a bunch of computers, you can just lease them, run a bunch of simulations on the cloud. And Rescale really helps with that. Okay. How many simulations can be coupled with FLAC at the same time?
All right, so there should just be, I mean, so 1 instance of PFC can be coupled with 1 instance of FLAC. They're actually running in the same executable. They're running at the same time. So I believe that you can do 2 of those, which is what you could do. If you have a FLAC license as well, you should be able to have 2 coupled models running on the same machine.
Is there a material modeling support package for version 9?
I believe the material modeling support package has been updated, so it will work with version 9. I believe that there have not been very many modifications to the command structure, so the version 7 package should work with 9 as well. There really have been very few changes to commands. There's really been a big push for performance in version 9, right? So if you have specific questions about material modeling support package, though, Dave Padiondi is the creator and maintainer of that, and you should email him directly.
There will be an updated material modeling support package on the website for the end of the year.
Great. Thanks. This is Jim Hazard, our software manager. Okay, so by the end of the year, there will be an official version 9 material modeling support package.
But I expect, like Matt said, that you could run the version 7 one and it would just work. So
Yes, I'm 98% certain that that's the case.
Question about structural elements in PFC 2D. Essentially, they'll be the ones that Matt has mentioned, cable bolts, rock bolts or piles, and then liners and shells and things like that. How much faster is a relatively simple disk-based simulation compared to a rigid-based block simulation? I suppose disks are much faster, but how much faster?
Right, so it depends on if you're talking about 2D versus 3D, and it depends on if it's a bonded specimen or an unbonded specimen, right? So for granular flow, balls or disks, we call them balls, they're, for a large granular flow, it's going to be quite substantially faster, factor of 2 or more faster in general than using rigid blocks. And this has limited the utility of using blocks for a lot of people, but with the speed increases, it makes it a little bit easier. Disks will always be faster. Balls will always be faster just by their nature. They are as fast as you can get. So honestly, I would suggest if it's a large scale flow simulation, I would suggest we have added new constitutive models or contact models like the rolling resistance linear model. That model can be super handy to give you behavior of angular blocks through rolling resistance. You can get the same bulk behavior, right? And it goes much, much faster. So for the vast majority of granular flow simulations, I would suggest using balls or disks. It's just much faster, right?
Great. Tensile and shear cracks are well understood from ITASCA documentations. What does it imply if there are mixed fractures? How do they differ from classic ones?
Yeah, it's a good question. I mean, it's on the one hand, you can just see that as a modeling tool or as a modeling construct to have a mixed mode fracture in this case. I mean, technically what it's meaning is that one or more of the subcontacts, so each subcontact, you're getting when you do the equations of motion, or excuse me, the force displacement law for a contact with the Subspring network model, each of the subcontacts, you're resolving an increment of displacement at the subcontact location. Those are actually placed on a disk, those 3 subcontacts that are a disk that has the same area as the contact area, as the surface area between the 2 bonded blocks, right? And so you're actually resolving the motion at those locations, those subcontact locations. So not at the centroid of the contact or something like this, or the centroid of the volume of overlap of the contact, or between the rigid blocks. In that case, you're actually resolving at different locations. So each of those, you're doing the force displacement law separately, meaning that you could have bending at one location, which is resulting in a tensile failure, but another subcontact then could subsequently have shear failure, right? Because it was still carrying some force at that subcontact, and for instance, the mode of motion could have changed. What does it really mean? That's a good question. These mixed mode fractures, they tend to be very few of them relative to pure shear or pure tensile breaking. They tend to be in the regions of models where you're coalescing larger cracks together, right? And so you might expect that there is a mixture of tensile failure and shear failure happening in these regions. So that tends to be where they happen. They tend to be oriented in these UCS tests nearly vertically, not subhorizontally. I mean, that's really what I can say about them. Definitely I think it's a very useful modeling tool. What it means, though, at a broader scale is a good question, and I don't know that I guess I have a really good answer for that, other than it allows for mixed mode failure, which can happen at these areas where you're transitioning and you're coalescing cracks together. So.
Great. 3 more questions, and then we'll be done with the webinar. Is it possible that the rewritten computational engine may cause changes in the results of the same model run in version 7 and version 9?
So you shouldn't expect that the model gives the exact same response, even going from an update of version 7 to a different update to version 7. If we change the compiler, you can get different response. The model, the overarching response should be the same, but you won't get the exact same answer, right? So what we've done when we've done the rewriting of these engine components, is we took a version 9 that had, before the components were rewritten, so using one compiler and using the same data structures as in version 7, and we took this newly rewritten engine component, right? And I did very careful comparisons between model response, both quasi-static, so for bonded assemblies, and for unbonded assemblies, like granular flows, to prove to myself that they were giving effectively the same model response. Is it conceivable? Is it possible? I can't say it's impossible, especially because there are so many different bells and whistles that can change how you do the computations in PFC. All of those things had to be brought over to the rewritten engine components, right? That includes bricks. That includes what kind of damping. There's combined damping for rigid blocks, and that had to be brought over. Local damping. They're just we also have time step scaling, density scaling, automatic time step, fixed time step. All of these are different kind of permutations on doing cycling. I've tried my best to make sure that they all work the same. I cannot guarantee 100% that there might not be something that's different, of course. If there is, though, please tell me so I can look into it. That's what we're here to do. But I'm quite confident that the results are the same and that the engine is doing the same thing for the vast, I think for all cases, but I can't say that 100%. I think for the very vast majority, it is doing these basically the same exact computation.
Great, thanks, Matt. Second and last question. If I track several variables in PFC 7 that depend on ball dot group, and also track some ball dot velocity of certain balls, for example, is PFC 9 not for me? He says, I do not understand very well what the restrictions of version 9 was with respect to tracking. I'm wondering if that is really the GUI and
the user interface, maybe. Yeah, I think that's kind of my take, is that that's on the user interface. You're allowed to have as many plots. If we're talking about plots, you're allowed to have as many plots as you like. The only thing that we've limited is the number that are being rendered at any one time. So there was by how you have the user interface split, right? So you could still have 20 plots if you want to. It's just that in PFC version 7, what would happen is there tended to be a memory overhead with having all of these 50 plots in tabs. Say if I had 50 plots, there was a big memory overhead that PFC 9 doesn't have, which is actually helps it be more responsive, helps the user interface in general be more responsive. That was one of the reasons for the rewrite. So there's no limit in the number of things that you can see, the number of plots you can have. There's absolutely no limit. There's just a limit on the number that are being rendered and held in memory at any one time, if that makes sense.
And I'll just add, you can still track, those fish functions still exist. You can still write your own fish functions or Python functions and track all of that information. With the new user interface, you can add those to watch lists so that you can track them right in the user interface without having to execute a fish function, for example. And then, as Matt mentioned, you can plot any of those charts, and so there's no difference from 7 to 9, or no limitations. In fact, 9 really expands that ability to track through the watch list and all the information that you can see in the new user interface. And then the last question. How long would it take to run, this is a hard question, the tunnel BBM with 165,000 rigid blocks?
In version 9, I don't exactly know off the top of my head. And of course, it depends on the hardware that you're using as well. The computational time, though, is consistent, with version 7. It's definitely faster, as I said, with version 9. Before the data structure changed to what it is now, it's faster to run the tunnel BBM model. That whole model, if memory serves, and this is just, I could be wrong, I mean, that whole modeling process, which starts from having a box, making a tetrahedralization of that box, cutting a tunnel, going through the whole process, that whole model, I think, runs on the order of in the low number of tens of minutes, maybe 15 minutes or 20 minutes or something like that, if memory serves. That's on my laptop. Of course, results vary. The running time is pretty much, isn't drastically different, right? As I said, the rigid blocks are a bit challenging, especially the bonded part, to make go a lot faster. They go really fast relative to 3-deck simulations right now. The data structures were largely optimized in the first place for bonded block modeling specifically. And they're, instead of being so cache heavy, which is what balls were, really it's memory, which is your limiting factor. And that's why they go so much faster with the rewrite in the data structure. Rigid blocks are really limited by the CPU because the computations are really heavy, right? So it's a sort of different use case. And it depends on if you're doing dynamic versus quasi-static. So again, it's a work in progress, and we're continuing to try to improve performance all the time. So beyond that, if you want to contact me specifically, or as Dave mentioned, you can get a 2-week license right here. So you could run the same model in version 7 and version 9 yourself and compare. But you can definitely email me directly if you have specific questions too.
Great, thanks, Matt. I'm sorry, someone snuck one last question in. Can fish functions be sped up if a supercomputer is used in the new version?
So fish functions in version 7 were sped up, I believe it was in version 7, through the introduction of the operator, fish operator, instead of a fish define statement. And that allowed you to run multi-threaded computations in fish, right? Which are limited. It doesn't, in a sense, limited for what you can do. You can loop through and do computations, or things that are atomic to something in a loop you can do in a multi-threaded way. That has sped up fish a lot. PFC, though, there is not a massively parallel version of PFC to be used on a supercomputer, right? So would it speed up fish to use on a supercomputer in PFC? No, because there's not partitioning of a PFC model onto different shared memory processors, which is what you would get on a supercomputer, right? PFC still runs on a single desktop machine, right, on a single CPU. That being said, with the performance enhancements for a lot of the types of simulations that I see people are doing, it runs a lot faster. So, but no, fish will not be sped up on a supercomputer in PFC.
And I'll just add, if you're not using the multi-threaded fish that was introduced in 7 and is in 9 with lists and splitting and operators, you really should be. And PFC tends to be more dominated by fish functions and some of our other software. And if definitely look into it. We have webinars, and there's a lot of good information in the documentation and examples. But if you're not using multi-threaded fish, you really should be. It's a dramatic performance increase in working with fish. And then the last comment is just thank you so very much for all the valuable information in your answers. PFC is getting to a different level! Exclamation mark. So thank you very much, Matt, for your presentation and all your answers to questions. Thank you to everybody for attending the webinar and participating. Thank you for your great questions. So we hope we've been able to share with you what's new and exciting in PFC 9. And if you have any questions, technical questions, feel free to email Matt. If you have any licensing or purchasing questions, contact our sales team. Thank you, everybody. Have a good day.
Thank you.